Hello everyone and welcome back. Today we're going to continue our discussion of multiple regression and discuss some alternatives that may be used in model building compared to the least squares regression model. Up to this point we've actually discussed several different ways to construct a multiple linear regression model via the least squares regression minimization problem. In particular, we've learned how to use that particular model structure to solve the multiple linear problem, polynomial regression, and also how to deal with categorical variables, interaction terms, and a combination of all of these in the same exact model via least squares regression. So let's just briefly go over what least squares regression actually does. So the least squares regression model least squares regression, which I'm just going to abbreviate as LSR, and some people will use ordinary least squares to approximate or to denote the same exact model, and it's perfectly fine if you do that. So the least squares regression model is to approximate beta 0, beta 1 down to beta b with these beta hats, beta hat 0, beta hat 1, beta hat 2 down to beta hat p, and the goal of least squares regression is to minimize a particular functional of those beta hats where that functional is equal to the sum from k is equal to 1 to n of the squared residuals, in particular yk minus y hat k, the quantity squared, or in vector form, the vector y minus x beta hat, the magnitude squared. Right, and that's the least squares regression problem, and it of course has a beautiful solution representation provided that the matrix xtx is invertible, in particular beta hat, will be equal to xtx inverse times xty, right, which we've proven already. Now, one can say, okay, well, what is so special about the least squares regression? Obviously, there are several other things you can minimize or maximize, or some constraint optimization problems and so on that you could use. So what's so special about this particular method? Well, obviously there's going to be several different things. In particular, we know that this is an unbiased estimator of beta, and in particular, it's a linear unbiased estimator of those beta values, where here beta hat and beta are vectors of those beta 0 down through beta p's, right? Now, there is one theorem, and it's referred to as the Markov-Gauss theorem, and the Markov-Gauss theorem says that the least squares regression approach, or the ordinary least squares approach, actually has the lowest sampling variance within all of the class of linear unbiased estimators for these particular model parameters, right? And obviously, the lower the sample variance, obviously the more accurate these things typically become as you increase the sample size to infinity, or the population size n, if you actually know it. Right, but of course, if you do not mandate that the estimator's beta hat tilde or something like that is not a unbiased estimator, obviously there it's possible to have a lower sampling variance. But of course, if you want the lowest sampling variance and unbiasedness, the ordinary least squares, or the least squared regression model, is the ideal case in that particular design, right? But sometimes we're willing to sacrifice a little bit of unbiasedness for a little bit more accuracy if we know a bit more information about our model. And that's why we're going to introduce some alternatives to least squares regression that I think are a little bit worth it to at least know about in your research. The first class of alternatives to least squares regression requires us to introduce a concept known as the Tikhonov matrix, which we're going to represent by G. Some literature and sources will use the capital letter gamma, but I'm going to avoid using the capital letter gamma here since we use that for the gamma function, which has its own applications here and there throughout statistics and probability, right? So we're just going to be using G here to represent a Tikhonov matrix. So obviously there's several different types of matrices that one can choose, but in this particular case, one typically chooses capital G to be a p plus 1 by p plus 1 matrix that also is invertible. right? In particular, we want it to be invertible because this matrix GTG also needs to be an invertible matrix as well. So if G is invertible, GTG will also be an invertible matrix as well. Now, some people will drop that the matrix G be a square matrix. And in particular, if you want it not to be a square matrix, you can sort of alleviate this particular criteria, but this must be satisfied. So the number of columns in this matrix must be p plus 1, but you have a little bit of flexibility on how many rows this particular matrix has. And when we actually state what this Tikhonov matrix is actually used for, you'll understand why you have that flexibility in just a moment. So the next class of methods that require this Tikhonov matrix is referred to as Tikhonov regularized least squares regression. So it's in some sense a generalization of the least squares regression, right? So we can call this, for example, the Tikhonov regularized least squares regression model. So the TRLSR approach. So what the Tikhonov regularization least squares model goal or aims for is to, again, minimize. So it's similar to the least squares. So minimize the functional f beta hat, which is going to be equal to, again, we have our y minus x beta hat squared norm, or our L2 norm. So that's just our least squares regression model, but it adds to this term and introduces our Tikhonov matrix G and then b hat the quantity squared, right? So our goal is to minimize the sum of squared residuals and in some sense the size of our beta coefficients. So obviously one can view this as sort of a penalty term for the beta coefficient sizes. So if it's too large, it's sort of going to have to restrict that magnitude, right? And that G sort of allows you to create some boundaries of sort of what you're going to allow your beta hats to be ranging from. Say, maybe you want it from minus 10 to 10, nothing bigger, maybe minus 5 to 5 or minus 1 to 1. Maybe you want to sort of restrict that boundary or that range for which your beta hat coefficients are sort of contributing to the value of your model. Obviously, that's going to have an effect on the accuracy of your model because obviously if that gets big, that has to get small for the same exact value of this minimization criteria and vice versa. So obviously we have some accuracy and some desire balance to work out here, right? But generally speaking, not always, but as you increase to the extremes of this process, typically the lesser the standard errors for these beta hats you will have, because as beta hat gets closer to 0, the standard error should also be getting close to 0 as well, hopefully. But that's also going to create a greater error sum of squares, right? So this is typically the outcome of what you're going to get from a Tikhonov regularized least squares regression model where G obviously is not the 0 matrix. So one special case of this class of least squares regression is what we refer to as the L2 regularized least squares regression. Right, and we can call this, for example, L2 regularized least squares regression, if you really want to label it something. Right. So what this does is it chooses a particular Tikhonov matrix G to be equal to a scalar multiple of the associated identity matrix, where this is a p plus 1 by p plus 1 identity matrix, and delta is typically chosen to be a non-negative scalar, right? So if that is our chosen Tikhonov matrix, and if you want to know what this matrix looks like, so G is going to sort of look like delta, 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 all the way down the diagonals with 0 elsewhere, right? So that's a diagonal matrix with deltas on the diagonal, right? So obviously, If delta is equal to 0, then this results into a least squares regression model, or an ordinary least squares regression model, right? So least squares regression is a special case of the L2 regularized least squares regression approach, right? Which of course is a special case of the generalized Tikhonov regularization approach, right? So let's look at that norm of g beta hat squared term, because that's sort of added to our error sum of squares term. So that's going to be equal to the norm of delta I times beta hat, the quantity squared. So delta is a constant, so that can sort of factor out. So we're going to have delta the quantity squared. So here you can see why delta shows to be a positive, because if it's negative, it's just going to square to be a positive number anyway. And then we're going to have the norm of the identity matrix times our beta hat vector. So you see why that number of columns needs to be p plus 1, because that's how many rows that this vector b hat has. And obviously I times beta hat is just going to be beta hat. So we're just going to have delta squared times the norm of beta hat, the quantity squared. So that's what this generalized representation sort of simplifies to in our model, right? So in this L2 regularized least squares regression, our goal is to minimize the functional f of beta hat is equal to the norm of y minus x beta hat squared plus delta squared times the norm of beta hat, the quantity squared. And you may see some people represent this as just lambda, just for short, because delta squared is just a constant, and obviously that's perfectly fine. But I choose delta because that's associated to the generalized Tikhonov matrix that one could choose, so that's why I choose to use delta squared instead of lambda in this derivation. All right, so that is that. So keep in mind, for the ordinary least squares regression line, so the ordinary least squares, aka the least squares regression approach, we had that beta hat is equal to xtx inverse times xty, right? So if we use this L2 regularized least squares regression approach, and some people actually give this a different name, sometimes we call this the Lasso, or no, the ridge approach, then one can actually show that the solution is actually pretty neat. So the ridge regression approach will solve this into xtx plus gtg inverse times xty. So that's the generalized Tikhonov, and that of course turns into beta hat is equal to xtx plus delta squared I inverse xty. So that's for the ridge approach, right? When you choose your g to be equal to delta squared I. So what exactly are we doing to our original matrix that we had before? So what we're doing is we're adding delta squared to the diagonal elements of xtx. And obviously when we invert that matrix, that new xtx matrix, since those numbers are bigger, then those values on the diagonal should become a little bit more smaller and smaller. So what I want to do to sort of illustrate what's going on here for this ridge approach for regression is to just give you a basic model to sort of get an idea of what's going on here for various values of delta. So let's assume we're building a model with two predictors, x1 and let's say x2. And obviously you can perform a simple linear regression model or a multiple linear regression model since we have two predictors here with no big deal. So let's assume we have our delta value. Now let's assume we start with a delta value of 0, right? So a delta value of 0, let's pretend that that is associated to a p-value for our model of, let's say, 3.06 times 10 to the minus 78. And let's assume that the condition number for your design matrix x, not xtx, but if you do xtx, just take the square root of that to get the condition number for x. Let's assume that's equal to 12,366.04. Now, obviously, if we have a p-value that small, 10 to the minus 78, that's quite small, Obviously, we're rejecting the null hypothesis, right? So how do we interpret that? Obviously, we're rejecting the null hypothesis that beta 1 and beta 2 are both equal to 0, which means our model appears to be appropriate. But when you see this condition number for that particular design matrix X, that's quite big, right? So if you require extremely good precision, that might cause you to have ill-conditioned matrices and hence non-precise calculations and hence a non-stable model, right? So obviously, when I choose delta to be equal to 0, this is obviously our standard ordinary least squares or a simple linear regression model. So if we do a Tikhonov regularization where g is set to be equal to, for example, delta I, then we can vary this variable delta to be larger and larger and larger. So, and if you don't know where these numbers are coming from, that's perfectly fine. These are associated to some random vectors that I sort of just wanted to illustrate with. So I'm fixing my x1, x2, and y data, and that's the p-value and kappa that I got for that particular model. So what I got for my delta, when I chose delta to be equal to 25, so my p-value changed into 5.13 times 10 to the minus 17, and my kappa value decreased to 56.13. Right? Now notice how much it changed in terms of stability. That should make you very happy. Now one could ask, well, why is my condition number so high for the original matrix? Well, that could be due to quite a few things. Large sample size, interaction terms, structural multicollinearity, several things, right? So in this particular case, it actually dropped quite a substantial margin. But do notice that our p-value increased. It's not as small as before, but it's still generally small. It's less than 5%, for example. So even though our p-value has increased, it's still under some reasonable level of alpha, say 5%. But notice that our stability dramatically decreased, which is a good thing. So there's obviously a trade-off. So there's a trade-off between model accuracy, and model precision. Obviously, our precision is getting better because our condition number is decreasing, but our model accuracy is decreasing because our p-value is increasing. So make sure you get those concepts in the right order in terms of their interpretation. So what happens when I increase it to, for example, 50? So do these kappas and these p-values change linearly? Actually, no. So one can find that this is about 7.75 times 10 to the minus 5, so 0.12340.775. So now we're into some reasonable small numbers, but it's definitely getting closer and closer to that typical 5% cutoff. And for our condition number, it actually doesn't even decrease by a factor of 2 here, even though we doubled our delta here. Right, so you can see the substantial change from 0 to 25 in terms of our kappa, but notice that I doubled my delta and I didn't really get that much of a kappa change here, right? But notice that my alpha value, my p-value is definitely increasing. Not as fast as it did from 0 to 25, but it definitely still is increasing, right? So if we increase this to 75, one could find for the random data that I selected was 0.1863 and condition number 18.73. So you could argue, okay, that's bigger than 10%, for example. Let's assume that's your alpha value. Therefore, you could say that a delta value of 75 is too extreme. So you would probably have to find some number in between 50 and 75 that sort of reach right before your cutoff value for your alpha, and definitely only work with delta values before that to sort of give you whatever condition number you're okay with. And let's just push this to the extreme just to see what it came out to. So if you choose a delta value of 100, one can find that that's approximately equal to 0.99999, and this is about equal to 14.07. Obviously, if you see a p-value closer to 1, that means we're failing to reject the null hypothesis with certainty that all of those coefficients are 0, which means the model is practically useless for predictions. Yes, the condition number has decreased, but keep in mind, the minimum value that the condition number can be is 1, so one can argue that this is not even close to 1 in terms of how fast this is decreasing, so definitely a delta value of 100 is extremely bad. 75 would be arguably be bad, and you can probably choose some beautiful number in between, say, 25 and 50 in order to choose your beautiful delta value to be working with for this model if you choose to do so. So up to this point, we've discussed these three models in a bit of detail. The first being our classical least squares regression model, which minimizes the error sum of squares. The Tikhonov regularized least squares regression, which minimizes the error sum of squares, plus this penalize term for the size of our coefficients beta hat. And then ridge regression, which is a special case of the Tikhonov regularization least squares approach, which minimizes based upon a Tikhonov matrix of a scalar multiple of the identity matrix, which is just delta I, which then reduces to delta beta hat in our G beta hat form and our general class number 2. Right? Now, obviously, there are several other things you could sort of add onto this list, but this is, of course, just a starting point. You could experiment with others if you want to. The fourth method that I want to introduce is referred to as the least absolute deviations, least absolute deviation regression, which you can just abbreviate as just LADR. So the least absolute deviations you probably are already familiar with, but its goal is again an optimization problem. So what this does is it aims to minimize f of beta hat, which is equal to the sum from k is equal to 1 to n, of the absolute difference between yk minus y hat k. So this actually looks quite a lot like the least squares regression, but instead of minimizing the sum of squared differences, it minimizes the absolute difference between the predicted and the obtained values in a regression model. Right? Now, obviously, you cannot use the typical quadratic optimization methods that you may have learned in an optimization class because this function, generally speaking, is not differentiable everywhere on its domain because absolute value functions have a corner at their vertex. Now, there are a couple downsides that I want to mention for this particular model. One is that the analytical solution for beta hat, i.e. beta hat is equal to something, doesn't exist. Right, so there's no cute formula. So you have to use numerical methods in order to approximate the beta hat values for this particular minimization problem. And two, there are potentially many solutions for beta hat. So for the least squares regression and the Tikhonov class, the solution exists and is unique, provided that that matrix XTX is invertible, of course. But even if that XTX is invertible, it's still possible to have infinitely many solutions for the least squared absolute or the least absolute deviation regression approach. So one could ask, well, if these two are downsides, what's the point in even introducing 4? So if you remember something about robustness, robustness is the ability to not change a lot when an outlier is introduced into your data. So if you are sure that your data does not have any outliers or potential outliers in your model, which is hard to pick up on, especially if your data set is big, then you probably wouldn't be using least absolute deviations in the first place. But if you aren't sure if there are outliers in your data set, the least absolute deviation regression model might be more robust, or typically will be more robust, right? i.e. it's not as sensitive to outliers compared to the least squares regression approach. Now, another method that is closely related to the least absolute deviation regression model is the following. Right, so we have our least squares regression model, we have our Tikhonov class, We have our ridge regression, we have our least absolute deviation regression, and the fifth is what we refer to as the lasso regression. So lasso regression, again, tries to minimize something. And what does lasso stand for in its context here? So lasso stands for, or is short for, the least absolute shrinkage and selection operator. Lasso, lasso, right? But generally speaking, the lasso is just another model that seeks to minimize another functional, but its goal is to minimize the functional f of beta hat, which is equal to y minus x beta hat, so that term should look familiar, plus some constant, let's call it delta, times the sum from k is equal to 1 to n of beta hat k, right? So it's the sum of the absolute values of your beta hat k. So in some sense, this also penalizes, so it penalizes the size of our beta hats, just like the Tikhonov regularization did, but it penalizes it in an absolute value approach, similar to the model that I just talked before. So again, the closed representation form does not necessarily always exist for the Lasso regression model, but again, you can always use some optimization toolboxes if you have availability to use them in whatever language you're working with. So up to this point, we've discussed the least squares regression model approach and four alternatives. Now I want to introduce you to just one more. So let's just refer to or review just a couple basic things about these matrices that we're working with. In particular, y is an n by 1 vector, x is an n by p plus 1 matrix, where p is the number of predictors, not counting your intercept, and obviously beta hat is going to be a p plus 1 by 1 vector. Again, that ranges from beta hat 0 up through beta hat p. So now what we're going to do is we're going to define a new matrix, and this matrix is going to be called a diagonal weight matrix. A diagonal weight matrix. So this matrix, which we're going to denote by W, is going to be a p plus 1 by p plus 1 matrix. So it's similar to, maybe some other matrices that you've seen before, which I'm not going to bring up here. So W is a p plus 1 by p plus 1 matrix, and it's going to be obviously a diagonal matrix, and it's going to have these elements W1, W2, all the way down to W, obviously, p plus 1, and 0 elsewhere in this matrix. Right? And we're going to define the vector W hat to be equal to W hat 1, W hat 2, all the way down to W hat p plus 1. So if you have 10 beta hats, you're going to have 10 W hats. So the sixth method of regression that I want to mention here is what is known as the Garotte regression. Garotte regression, right? And this is what we refer to as a constrained optimization problem. And there are two variations to the Garotte regression that are commonly used. So the goal for Garotte regression is to minimize with respect to W hat, not beta hat. So its goal is to minimize the norm of y minus xw beta hat squared, right? Where beta hat is the beta hat that is obtained from the least squares regression model, or the ordinary least squares approach, right? Now, that is the overall function that you want to minimize. Then we add two constraints. So there's going to be a couple constraints we want to minimize subject to, right? And if you don't know what I mean by constrained optimization, sort of think about it from this perspective. Let's assume that we want to minimize the value for which this parabola attains, right? So we want to find the minimum value of y that minimizes this particular quadratic, right? Which is obviously f of x, right? So some people would say, okay, obviously the minimum value is going to be there. But let's assume that we want to minimize with respect to the constraint that all of the values might be above must be above this line, right? So it must be in this shaded blue region. Obviously now, the solution now will be this point there, which is obviously quite different from the original. So that's what we mean by constraint optimizations. That would be, for example, one constraint, but you can obviously have as many as you want, right? So constraint version number A, or version A, is that WTW, which is obviously the same thing as the norm of W squared, and we're referring to W hat as the point estimates for W, must be less than or equal to C, where C is typically taken to be some real number constant. Obviously it should be greater than 0, but you can take it to be equal to 0 if you really want to. This is known as the standard Garotte regression. Right? So minimize this functional with respect to that constraint. Now, there is a second variation, and it says that these weights must be all greater than or equal to 0, and the sum from k is equal to 1 to p plus 1 of these weights must be less than or equal to some other constant. Let's call it, for example, C2 or CA and CB, right? So these two problems are different. So we can either minimize subject to this first constraint, that's called the standard Garotte regression, or we can minimize that functional with respect to the second constraint, and that's called the non-negative Garotte regression. And you could say, well, why would you want to choose these constraints to minimize? Well, obviously we don't want the beta hats to be too big, but instead of penalizing the beta hats, now we're penalizing in some sense the weights that we assign to each of those beta hats for our model, right? Which is in some sense the same, but it of course has some theoretical and model differences, which I won't get into here. Right, but these are all 5 variations that you could consider when exploring alternatives to least squares. Now, there are obviously some others, which I'm not going to get into here. For example, you could do a weighted least squares regression model, which in some sense is a more easier version compared to the Garotte regression. The second version is what is referred to as the partial least squares regression, and another one is known as the principal components least squares regression, all of which we may get into a little bit later on, but I just wanted to mention these alternatives to least squares regression now because it's definitely important to keep in mind that there are other ways to solve problems if there are other desires you need for your model structure. So I hope you enjoyed this video, and I'll see you in the next one. Take care.